So, hi and welcome everybody to the lecture titled Error Control Coding. In today's lecture, we will be talking about channel coding mainly and the purpose of using it and its importance. So, basically, it's gonna be a very important lecture that I want you to give too much attention to it because it's one of the most important concepts that we usually deal with in wireless communication and in communication in general and even storage. So the outline of the topic, we will be discussing several topics related to error control coding, and it's kind of a subclass, sub-course within the main course of communication. So mainly we will be talking and discussing about the concepts, the linear algebra behind error control coding, linear block codes, and cyclic codes and PCH codes and the differences from RS codes, convolutional codes with RIP decoding, trellis decoding, turbo codes, and LDBC codes. So it's going to be very comprehensive topic, but mainly in this lecture and next one we will be covering the basics of error control coding. So what's error control coding in communication and storage? So we already discussed in the previous lectures related to communication systems that when you transmit your data over a channel, the channel in most of the cases is noisy. And since it's noisy, you are not sure you are not sure whether you will receive your data bits correctly without any errors, or sometimes you will have some errors in them. So the point here, how do you detect these errors and correct them? Because at the end of the day, you need your transmission to be reliable from the transmitter to the receiver. And you want to make sure that this transmission is being held with less number of errors, with minimal number of errors. Error control coding, this new subject, is responsible for the control of errors so that efficient and reliable data transmission and storage is possible. So in 1948, Shannon, who's a scientist, was working on information theory and communication and the math behind communication systems, showed to the world by one of his papers that by the use of proper encoding of the information, errors introduced in a noisy transmission channel or a storage medium, when you store your data on a disk, on a floppy, on a hard disk, hard drive, on a cloud, wherever, the information can be, the error in the information can be reduced to any desired level without sacrificing the rate of information transmission or storage, as long as the information rate is less than the channel capacity. This was the conclusion in a study conducted by Shannon in 1948, that you can design encoding schemes that can reduce the errors that occurred due to noisy channel to a very low level without reducing the rate of transmission, as long as the rate of your transmission is below the channel capacity. So this was the theory. The theory is saying you can design these codes in such a way that you avoid the effect of the channel, especially the noise. But how to design them? This is the question. How to design them, this is the responsibility of researchers, engineers, scientists to come up with practical design for encoding schemes that can avoid the errors caused by the channel. Now let's have a look at the most basic block diagram that we usually use for error control coding. You have your message, which is composed of data bits, zeros and ones, ones and zeros. And you have after that source encoder. The responsibility of source encoder is to compress your data bits and make sure they are not redundant, and in order to reduce the size of your data, and therefore you you use less memory. And after source encoder, you use channel encoder. Channel encoder adds redundant bits to your message data, and these redundant bits, we call them the parity bits, and they are responsible for protecting your data from the noisy channel, so that you can receive all your data bits successfully and conduct your transmission in a reliable manner. After the channel encoder, you have modulator. The modulator, which are the topics that we have been discussed so far in the lecture, whether usually digital modulator like QAM modulation, PSK, FSK, binary phase shift keying, so on and so forth, or any other modulators. And then you transmit over the channel, and there is noise added to the channel, and then at the receiver side you need to use demodulator, then channel decoder, and then source decoder, which is after that the message estimate. You estimate your message, which is supposed to be equal to the transmitted message. So in today's topic, we will be talking and discussing and explaining and like dealing with this block called channel encoder. So here you have the source output. The source output here, the output of the block called source encoder is U. And this U is a vector of zeros and ones. Vector. Let's say 100 bits in it. And this we call it the information sequence. The encoder output, the channel encoder output, which is denoted by V, is called the code sequence. And the demodulator output sequence block R at the demodulator, you modulate it, you transmit it over the channel, and then you demodulate and you receive R. R is called the received sequence. So we have the information sequence U, the code sequence V, and the received sequence R. After the channel encoder, I must be able to get U, which is estimate U hat, which is an estimate of the information sequence. Yes? Ideally, U hat is a replica of U, although the noise may cause some decoding errors. Yes? U hat is basically what you transmitted at the transmitter. It's U. But since you have some noise and estimation errors and due to some other functionalities, U hat and U sometimes they are not exactly the same, and that's why we plot the bit error rate or some diagrams or curves that shows us the difference between the transmitted sequence and the received one. So here is the block diagram. Again, in most coded system, U, V, and U hat are binary sequences. They are zeros and ones. If the demodulator makes hard decision, R is also binary. R is binary. Hard decision, I mean the demodulator just decides yes or no. Is the bit above 0 or below 0? If it is above 0, means it's 1. Below 0, minus 1. That's why we call it hard decision. A good code is designed to minimize the probability of decoding error. Yes? The code that we want to design is a code that can minimize the probability of error. How do you calculate the probability of error? It's the probability that the received information sequence you had is not equal to the transmitted information sequence U. So basically you try to find what's that probability. So noisy channels, let's give you some examples on noisy channels. Where do we see these noisy channels? In phone lines, yeah? Transmission channels like phone lines, mobile cellular telephony, high frequency HF radio, microwave and satellite links. Satellite links, for example, your TV. the dish on your home receiving signal from the satellite. The main source of errors is due to noise. Optical fiber cables as well. And the noise disturbances can be due to thermal noise, crosstalk, switching impulse noise, and these are the main noise disturbances in the channel. Now, this is regarding the transmission. Yes, this is the noise affecting your transmitted data. But what about when you store your data in a storage? When you store your data in a storage, like core and semiconductor memories, magnetic tabs, drums and disk, compact disk, optical memory units, cloud, hard disk, SDD, SDV, whatever, those also are affected by noise. And this noise, the disturbance here is surface defects or dust particles. And both are the goal here, although transmission systems are related to communication science and storage media is mostly related to computer science, but both of these are basically trying to use error control coding in order to reduce the amount of mismatch between the transmitted information sequence and received information sequence. This is a simplified version of the previous block diagram where we have just digital source and U is the information sequence. After the encoder we have the code sequence. Then you have the channel. You have R, the received sequence, and then decoder, and then the digital sync. So the main engineering problem here is to design and implement the channel encoder decoder pair. The main problem here, or your goal as an engineer, is to design the encoder and decoder pair, we call them pair, in such a way that the information can be transmitted in a noisy environment as fast as possible. The message can be reliably reproduced at the output of the channel decoder. Here, U hat is very close to U. And third, the cost of implementing the encoder and decoder falls within acceptable limits. What does this mean? This means that you don't increase the complexity. The complexity of your decoder is low. Why don't we like complex decoder? Because complex encoder and decoders, they cost us money in terms of delay and power and the processing. And in the future, we are mostly going to be using Internet of Things devices, which are limited in memory, limited in size, limited in power, limited in processing capabilities. So we want to reduce the complexity of this encoder and decoder as much as we can so that we don't increase the overall cost of the system. Because if you increase the overall cost of the system, your system will become very expensive to a level that nobody can afford buying it. Customers, companies will not be able to sell it to people, and people will not be interested in buying it because it's very costly and expensive. So as an engineer, yes, you need to design something that's workable, that can achieve the goal and task of transmitting your data in a reliable manner, but also without increasing the cost to an unbearable level. Yes? So this is what we are aiming to achieve basically when we design the codes. What are the types of codes? Depending on the encoding structure, error correcting codes can be categorized into the following two classes. Block codes or convolutional codes. Block codes, they work and operate on block by block, while convolutional codes, they work and operate on bit by bit. Yes, it's sequential operation on bit by bit. You take the first bit, operate on it, get the output, then the next bit, next bit, next bit, and so on. While block coding takes block of bits, like let's say vector of 10 bits, 20 bits, and we try to, from this block of 20 bits, which we call the information sequence, we get a corresponding coding, a corresponding code word sequence that represents this information. But this code word sequence has some redundant bits in it. We call them parity bits that we can use in order to reduce the amount of errors and detect the errors, and if we detect them, try to correct them so that we make sure we receive our data reliably without any errors caused by the channel. So for the block codes, the encoder of the block codes operates on k information symbols at a time. On k information symbols at a time together takes them. A message block is represented by a binary k-tuple. For example, you have your u, which is u0, u1, uk minus 1. U is vector and u0, u1 can be 0 or 1. The encoder transforms each message u independently into an tuple v. After the encoding process, you get v. Now v is also binary sequence, zeros and ones, but the length of v is greater than u, and it's like usually n, the value n is greater than or equal k. There are, now if you have, let's say, k number of digits for your message, then there are 2 to power k different possible code words corresponding to 2 to power k different possible messages, yes? If you represent this, your message by binary, 8 binary digits, yes? Then how many different possible messages you can get? How many different possible messages you can get? You can get 2 to power k, whatever k is. Now we call the ratio of k over n the code rate, and we denote it by r capital equal k over n, and we call it the code rate, and this is usually less than 1. Why it's less than 1? Because n is usually greater than k. The number of bits after the encoding is more than the number of bits before encoding. For a binary code, in order to have a different code word assigned to each message, we have k, the k number of bits in the information sequence is less than the number of bits in the encoded sequence, and therefore r is usually less than or equal 1. If r is equal 1, this means that the length of the encoded sequence is the same as the length of the message itself, and we call that the information rate is the same for the message and the encoded sequence. They are the same. Now let's put this in action and go and take example. You have your messages here. Suppose your message block is composed of 4 digits. The message sequence length is 4 bits. Then how many different possible messages you might get? 16, because 2 to power 4 is 16. And you start from 0000 to 1111. And after, this is you. This is the message is you. After you encode it using the block encoder, you get a code word of length 7 bits. Now, as you can see here, the message itself, you put it at the beginning, at the end of the code, and then you put some other bits, like this message. Let me open the marker so that you can see it more easily. Now with the marker you can notice it, hopefully. So you have your message bits. Here is the marker. This is the message. And this is, we call it U. You put this at the end of the code word here. It's the message U. And then you put here some other bits. This is V, this is V, this is U. So when the message content is shown in the code word clearly, we call the encoder systematic encoder. When the message signal is not shown in the code word, we call it unsystematic. We usually prefer to use systematic because it's easier to deal with and it's much more desirable at the receiver side, especially in the decoding phase. Now let's go to the next message. It's 0001. You put it here, 0001, and you have some other bits here you add. How do you get these bits? You get these bits based on a generator matrix. This generator matrix, it works like a transform. And this transform is dependent on some basis function, independent vectors, and the data. Based on the data values, based on the message bits, you get these values. The message bits get multiplied by the generator functions. Let's say you have four basis functions, like this. And the length of these basis function, and you have your vector here, message. Your message gets multiplied by the vector and the result is 1 bit. By the next and the result is 1 bit. These bits, you put them at the end of the message. We will talk about them in detail, but for now, let's just understand that the message systematic encoder puts the message bits themselves in the code word. And the other bits, we call them these bits 3, 3, 3 here. Because here, for example, the message, this one is basically this one, exactly. And the other bits, those one, we call them parity bits. Those are, why do we add these bits and how do we obtain them? Using generator matrix, like a transform matrix that depends on the input and independent basis function. And what are these bits? Parity. Why? How do we use them? We use them to detect if there are errors on the message signal. This is how the block code basically works. Now let's move on. The code parameters are k equal 4 and n equal 7. In the k is related to the message sequence and n is related to the code word length. N is equal 7. Therefore, there are a total of 2 to the power 4 equals 16 possible messages and code words chosen out of 2 to the power 7. Here is the thing. Here we have 16 messages, yes? But because 2 to the power 4 is equal to 16. But when we map 4 to 7 bits, in 7 bits, how many different messages we get? We get 2 to the power 7, which is equal to 128. True? 128 bits, 128 different possible code words. This is what you will get from the 16. But from these 128, we only select 16 of them to represent the 16 messages here. At the receiver, when you transmit them to the receiver, how would you know which 16 code words you have used? Due to this process, the receiver can make some mistakes in deciding on the code words, and therefore we need to limit the decision to only certain set, and this is what we usually consider at the receiver, and this will be evident and very clear for us when we explain this in more details in the coming slides and give you some examples. But keep this point in mind that code words have larger number of possibilities while a message list, and this larger number of possibilities you only need to select a few of them, and the remaining they cause kind of randomness, and this is not desirable at the receiver side, especially in the detection process. So that was about block codes. What about convolutional codes? The encoder for the convolutional codes operates on k information symbols at a time. A message block is represented by a binary k-tuple. U is given as follows. The encoder transforms each message U into an n-tuple. V is given as follows, which is the output of the encoder. The encoder is said to have a memory order of M if each encoded block depends not only on the corresponding message block but also on M previous message blocks. What does this mean? This means that for each input bit from the message, you produce certain number of output bits. These output bits, each one of them is dependent not only on the current value but also on some previous bit values. And therefore we call this memory encoder. It has memory. Memory means it stores some values in the encoder because the output bit will be dependent on them later on. The ratio R is K over N is called the code rate, similar to the block code type. So there is no much difference here, but here it operates on bit by bit and you have memory. Give you an example of a structure. So the structure looks like this. You have U, you have U, you have V, you have delay element. The delay element are the ones in the square here, and the exclusive OR gate is given at the output of each bit. So consider the information sequence U equal 10110011 with the leftmost bit assumed to arrive at the encoder first. This means that this bit enters the encoder before the other bits. So basically you have 11001101 entering to the encoder, and this is U. You are required to determine V. So at each time unit, k equal 1 information symbols enter the encoder. Only one bit enters the encoder. And N, the number of output bits, is 2. 2 code symbols are produced. The code rate symbols here represents bits because we are using bits. The code rate is R equal K over N. Now question, if for each input bit we are producing 2 output bits, what's the code rate in this case? The code rate R is equal to K over N. True? K is the input bit 1 and N is the output bits 2. So K over N is half, 1 over 2. The encoded code sequence is therefore given as follows. Now, how do you obtain this? For example, when 1 enters, you get this value 1 0. The next bit you get 1 1. Next you get it. How do you obtain this? How do you obtain this? Let's see. I said the value here, you have v here, yes? V is vector, and this vector is producing 2 bits. Let's call them v1 and v2. v1 and v2. This is coming from v1 and this coming from v2. And this is a switch, kind of taking this value, then this value, this value, then this value. True? And let's assume this sequence of bits is entering the encoder here. Yes, it's entering the encoder here, and we want to find the encoded bit V. So what will you do? What will you do? Tell me. You will take this bit 1 and push it to the encoder. So you have 1 here. What do you have here? 0. What do you have here initially? 0. Then the output V1, what would be the value at V1? V1 is equal to this, the value, the bit here from this branch, the bit from this branch, you take it, and the bit from this branch, you take it, and XOR them, exclusive OR gate. 1 XOR 0 is equal to 1. Yes? 1. Again, for V2, so V1 is equal to 1. For V2, how do you find V2? You take the bit at this position, and the bit at this position, and the bit at this position. As you can see, there are 3 arrows. So for V2, you come here, it's 1 XOR 0 XOR 0, and it's equal to 0 1 with 0 1, and 1 with 0 XOR 0 equal 1. Then the output V2 is also equal 1. So for when the input bit is 1, the first bit is 1, the output will be 1 1. So here this is 1, and the output here in V 1 1. Now let's say that 0 after 1 comes here. After 1 there is 0. So what do? You erase this 1 and move it here. 1 now is here after the delay. You put it here, and there is a new 0 comes into the circuit here. The 0 is here. So now you need to determine what's the value of V1 and V2 again. How do you determine V1? V1, you take the bit at this position and the bit at this position. The bit at this position 0 and the bit at this position 0. 0 XOR 0. 0 XOR 0 is equal to 0. 1 with, to remind you of this is XOR operation. Yes? So here you have 0 here and 0 here, you get 0. So V1 here is 0. Now what about the other branch, V2? You have 0 with 1 gives you 1, the result of this, and 1 with 0 gives you 1. So V2 here, this is V2 1, I found it 1, and V1 is 0. This is V1. let's take, so we finished the first bit 1, we finished 0. Let's take now the third bit 1. What will happen to the circuit? It will push these zeros one step to the right, because new bit is coming to the circuit, and we need to recalculate the value of V1 and V2 accordingly. So what will we get here? This one will move here to this, it becomes here 1, and this 0 will move here, so this becomes 0, and this is 1, 0, and then here the bit that's coming to the circuit is 1. So you remove this 0 and put instead of it 1. Okay? Now calculate V1 and V2. V1, you take the bit here at this position and the bit at this position. There are two arrows, and you XOR them. Here I have 1 and here I have 1. 1 XOR 1, 0. That's why I get here, this is V1 equal 0, and here 0. Now let's see the other V2. What's the value of V2? V2, you have 3 branches. 1 XOR with 0, 1, true, and 1 XOR with 1, here 1 XOR with 1, 0. That's why you get here also 0. V2 is equal to 0. Now new bit comes in, you need to shift this to the left again, to the right again. So here this one comes here to the 0, you remove this and put 1, and this 0 comes here, you remove 1 and put 0, and there is a new one coming here. This you removed it, new one is coming, new one, and you recalculate V1 and V2 according to the incoming information bits, and then you write this bit. So in the test or quiz or exam or whatever, if I give you a circuit like this, circuit, whatever, I can change this circuit a little bit, maybe increase the number of blocks. These we call them memory blocks, they cause delay. I can increase them or use only one and add more branches, remove some of the branches. At the end, I want you, if I give you an information sequence U, and this information sequence contains binary bit zeros and ones, and tell you encode this information sequence to a code word V that can represent my message in order to protect my data, to add some parity bits that can protect my data from the noise channel. By doing so, you can be able to find V that you need to transmit instead of U. So here you don't transmit U, the message signal, directly. Instead, you are transmitting V. Clear? I hope this is clear, because it's very important question, very important point. This is how convolutional codes work. Now let's move on. Types of errors. There are two types of errors mainly. In memoryless channels, what do we mean by memoryless? There is memory and memoryless. Memoryless means the output bit, the output in the channel, does not depend on the previous values. It just depends on the current values. So in memoryless channels, transmission errors are random in the received sequence, and memoryless channels are called random error channels because they are memoryless. This means that if you have a sequence, received sequence like this, then the channel affecting each one of these bits is independent between these bits from one bit to another. They are independent from each other. In channels with memory, noise, this is in memory list, the noise is independent from one bit to another. But in memory channel means that the output value depends on the current and the previous ones, like convolutional codes. Noise is not independent from transmission to transmission, is not independent from one bit to another. There is kind of correlation between them. Why? Because it's memory, it has memory. There is dependency on the previous bits. And the channel can stay in a bad state. For example, the channel can remain in bad situation for consecutive uses of the channel. For many different bits, the channel can remain bad. These channels are called burst error channels. You don't have one single error. You have consecutive number of errors located in certain sequence, and this we don't like it. It causes severe degradation and severe reduction in the bit error rate, severe number of bits. It increases the error in the system, reduces the reliability, and we need to come up with techniques or special coding methods that can overcome this. Okay, these are the different types of errors we have. And then what are the error control coding strategies we use? We use one-way communication systems. And one-way communication system means there is no retransmission. You just send once your data. And for this, we use forward error correction. There is no communication or feedback between the receiver link, the uplink, the receiver and transmitter. And this relies on automatic error correction. First, you detect and correct the bits. While if you have two-way communication systems, we use automatic repeat request, which relies in error detection and then try to superimpose the packets and enhance their reliabilities. Let me give you example. Which one is better? Here I have a transmitter and here I have receiver. Which one is better, to use forward error correction or ARQ? This is one-way communication system, this is two-way communication system. You tell me, it depends on the requirements of the system. If if your system or your application does not tolerate delay, does not tolerate like having any delay on your communication, like you are making real-time communication, real-time voice call, real-time video, sometimes something that's very sensitive to delay, then it's better to use forward error correction, because forward error correction just encodes the data and sends it once. However, if you can tolerate delay, some delay in your system, you can allow it. Then you can use ARQ, automatic repeat request. How does this work? Your packet, you basically transmit your first packet to the receiver. The receiver tries to decode the packet, receives the packet, tries to decode it. If the receiver finds some errors in the packet and he was not able to decode the packet successfully, then he declares error. There is error in the packet. Since there is error, he cannot go and use it for decoding the application or using it later on the upper layers. He asks the transmitter to retransmit the packet again one more time because the first packet was in error. So to do that, the receiver sends a NAC message. NAC message means I didn't receive the packet correctly. ACK message means acknowledgement, I received the packet correctly. And don't transmit the packet again, transmit a new packet for me. Based on this, you can keep retransmitting your data until you receive it successfully, or the maximum number of allowed retransmission are expired, are already used. So now let me ask you this question. Suppose you have two applications. One is FTP or web FTP application, file transfer protocol application, or web browsing, or mail like Bob mail or SMTP mail. Let's say mail. For these applications, which one of these coding is more suitable? ARQ or FEC, forward error correction? I think you already know the answer. ARQ is more suitable. Why? Because these applications, they do not tolerate any errors. They don't accept any errors. If there is a single mistake, a single error in the file you are uploading to the server or to the website, the file will not be accepted and it will ask you to re-upload the file. Yes? This is very critical to understand. What about web browsing? When you ask for a web page, if the web page cannot be displayed as whole correctly, it will not show you the page because it's very critical. What about mail? If you send a mail or message, do you tolerate any errors? You don't accept any errors. You tolerate delay, but you don't accept errors. That's why for these applications, mail, web, FTP, you use ARQ because you don't care too much about delay. You care a little bit more on the quality, the reliability of your connection. Now, on the other hand, let's say you are using voice communication, voice or VoIP, voice over IP, or real-time gaming or video. Which one of these coding techniques you will use? Forward error correction or ARQ? Forward error correction. Why you will use forward error correction? Because these applications are very sensitive to delay. It cannot wait for the receiver to decode the packet and then send an ACK or ACK to the transmitter and wait another time to transmit the packet one more time and then combine it and decode it. It causes delay, and voice and video, they cannot afford delay. So you give up on the performance, on the reliability a little bit for the sake of obtaining real-time communication with no delay. Okay, I hope you understood these now, the differences between them, how they work, forward error correction, ARQ, which applications use them, and what are the differences between them. Now, error control coding strategies. Forward error correction achieves the constant rate of information transmission and does not require a feedback channel. This is the most critical point. Does not require a feedback channel. Okay? There is no feedback channel. On the other hand, high reliability requires complex decoder. These usually use complex decoder, unfortunately. Okay? On the high required ARQ achieves high reliability with simple decoders, but requires feedback channel and achieves variable throughput and increases the delay. Okay, these are the two key differences between them and that we should be careful about. So now you have basic knowledge about error correcting codes, the differences between the memory channel and memoryless channel, the differences between convolutional codes and the block codes, the differences between forward error correction and ARQ, and what are the features of each one of them, and also not only this, but also for the applications that are using each one of them. So with this, you have some basic understanding and basic knowledge related to error control coding. We can stop here and continue in the next part that will come soon after this lecture, maybe after a few hours or few. Thank you very much and see you in the next part.